Now let's discuss part C. In part C, a horizontal uniform rod shown below has a length of 0.60 meter and a mass of 2 kg. The left end of the rod is attached to a vertical support by a frictionless hinge that allows the rod to swing up or down. The right end of the rod is supported by a metal wire that makes an angle theta of 30 degrees with the rod. A 0.50 kilogram block is also attached to the right end of the rod. Calculate the tension in the metal wire. So again we have a rod which has a length L of 0.60 meter. Mass of the rod is 2.0 kilogram and it is supported with the help of a metal wire which is making an angle theta of 30 degree with the rod. Then we have a block of mass MB which is 0.50 kilogram which is attached to the right end of the block, and we need to calculate the tension in the metal wire. So in order to find tension, we need to first understand what are the forces acting on this system. So first you have the force due to gravity acting on the rod. So we will call it FG1. This force due to gravity will be acting on the point of center of gravity, which is the same as center of mass for the rod. Then you have the force due to gravity acting on the block. So we write Fg2 for the block. Then we have the tension in the string. And since the rod is in static equilibrium, sum of torque produced by these forces must be equal to 0. So I can write net torque on the system is equal to 0. So let us first understand what kind of torque each of these forces produce. Fg1 and Fg2 are trying to pull the rod down, so they will produce a torque which is clockwise, whereas the tension force will produce a torque which is counterclockwise. Now when we say the net torque is 0, that means torque which are counterclockwise must be equal to torque which are clockwise. Now we calculate torque tau as Rf sine theta, where F is the force that produces the torque, R is the distance between the force and the axis of rotation, and theta is the angle between them. So let us first find the value of R for each of our forces before we substitute here. First force is the force due to gravity Fg1, which is acting at the center of mass of the rod. Since it is acting at the center of mass, its distance from the axis of rotation will be half the length of the rod. We call this distance as R1, and R1 will be equal to L by 2. Then the next force is force due to gravity acting on the block. Since it is located at one of the end of the rod, this distance, which we will call as R2, will be equal to the length of the rod. So we call R2 to be equal to L. Then we have the counterclockwise torque, which is produced by the tension in the string. And again, tension is originating from the point located at one end of the rod. The distance of force of tension from the axis of rotation, we will call it as R3. And R3 will also be equal to the length of the rod. Once we identify these distances, now we can substitute for torque. Counterclockwise torque can be written as R3 T sine theta equals. Clockwise torque is because of two different forces, so we will add the torque due to each of them. So first one will be because of Fg1, so R1 Fg1 sine 90, 90 because it's making an angle of 90 degree with the rod, plus the second force is Fg2, so R2 Fg2 again sine 90. I want to find the tension in the metal wire, so divide by R3 sine theta. We get T to be equal to R1, Fg1 I can write to be equal to mass of the rod times G plus R2. Fg2 will be mass of the block times G over R3 sine theta. So we can write this as T equals R1 is L by 2 M times G plus R2 is L MB times G over R3 again L sine theta. Now let's substitute. Length of the rod is 0.60 over 2. Mass of the rod is 2 kilogram. G is common in both the terms, so we can take it outside in the bracket. So I will take it out later. Plus length of the rod again 0.60. Mass of the block is 0.50. Multiply with G, so 9.81 over 0.60 times sine of the angle 30. And when you solve this, you get the tension in the wire to be equal to 29.43 Newton. Next, part D of the question says, the metal wire that supports the uniform rod is cut near the end of the rod. The rotational inertia of the rod about its center of mass is ml square by 12. Calculate the rotational inertia of the rod about the hinge. So this is similar to part B of the question, where we can find the rotational inertia about the hinge by using the parallel axis theorem. We know the rotational inertia about the center of mass, which we will call as ICM. And ICM here is ml squared over 12. And I need to find rotational inertia about the hinge, which is an axis parallel to the axis of center of mass. So we use parallel axis theorem. According to parallel axis theorem, I can find I parallel to be equal to rotational inertia about the center of mass plus mass of the rod times d squared, where d is the distance between the two axes, which in our case is L by 2. Now let's substitute. ICM is ml squared by 12 plus ml by 2 squared. That gives you, let's take ml squared as common. Here we have 1 over 12 plus 1 over 4. That gives you moment of inertia about the hinge to be equal to 1 over 3 ml squared. Now we can substitute the values here. 1 over 3, mass of the rod is 2 kilogram. Length of the rod is 0.6 squared. And when you solve this, you get rotational inertia about the hinge to be equal to 0.24 kg meter squared. Next, in part 2 of the question, we need to find the initial angular acceleration of the rod about the hinge. Now when you cut the metal wire, there is no tension force to support the weight of the rod and the block, and hence the system is no longer in static equilibrium. And if it is not in static equilibrium, there will be a torque acting on it, and that net torque you can write as I times alpha, where I is the total rotational inertia of the system. Now the forces producing torque is the force due to gravity acting on the rod, which we call as Fg1, and the force due to gravity acting on the mass, which we call as Fg2. And if I want to calculate alpha, I can rearrange this term and write it as alpha equals tau net over I. Tau net we can write as the sum of torque produced by Fg1 and Fg2. So we will write this as R1 Fg1 sine 90 plus R2 Fg2 sine 90. Rotational inertia I is the total rotational inertia of the system. So rotational inertia of the rod about the axis of rotation, which we found to be equal to I parallel, plus rotational inertia of the block. So I will write this as I B. R1 is the distance of force Fg1 from the axis of rotation. So this is R1, which in our situation, you can write it to be equal to L by 2. R2 is the distance of the block from the axis of rotation, and R2 is equal to the length of the block. The angle made by force due to gravity in both situations is 90, as they are perpendicular to the rod. So now we can substitute. R1 I will write as L by 2. Fg1 I can write as mass of the rod into acceleration due to gravity. Sine 90 is 1 plus R2 is L. Fg2 will be mass of the block into G over I parallel plus rotational inertia of the block we can write as mass of the block into the distance R2 squared. So let's substitute now. G we can take common for both terms, so I will write 9.81. Length of the rod is 0.60 divided by 2. Mass of the rod is 2 plus mass of the block is 0.50. Length is 0.60 over I parallel is 0.24 plus 0.50 times 0.60 squared. So that gives me the value of alpha to be equal to 21.02 radian per second squared.